Hi, I'm Chay Ryali. I'm going to be talking about how we built SAM2, a foundation model for promptable visual segmentation in images and videos. SAM2 is a unified model that has state-of-the-art performance on images and videos. On images, SAM2 is 6x faster than SAM1, while also improving on accuracy metrics. And on videos, it needs 3x fewer interaction than prior approaches. I'll be talking about how we built the model, as well as how we built a data engine that iteratively allowed us to improve both the model and data via user interaction to build the largest video segmentation dataset to date. Before we begin, I should mention that this is work done with a large and fantastic team, and I'm honored to be talking on their behalf. Let's dive in. Let's begin with a quick overview. We'll do a quick recap of SAM1, or just SAM for simplicity, talk about the challenges involved in enabling similar capabilities for videos. Then we'll talk about SAM2 and how we solve some of the challenges. And then we'll talk about some results. After that, we'll talk about some exciting updates to SAM2 and also the developer suite that we released. Then we'll talk about the launch and some exciting real use cases from the community. Let's dive into a recap of SAM1. SAM1 introduced a task, model, and dataset to enable the segment anything capability in images. We'll talk briefly about each of these. I should add that throughout this talk, having this framework in mind and explicitly thinking about the task, model, and data axes will be helpful. Let's talk about the task. The task is that of promptable segmentation in images. More specifically, the task is to select all of the pixels in an image that correspond to a specific object or a part of an object. And this grouping of pixels is going to be called a segmentation mask. And the object of interest is indicated using prompts, which can be clicks, positive or negative, bounding boxes, or masks, which are not very precise, or even text. The prompts can be user input, or they can come from another model, in the case of a composite model system. For simplicity, I'm just going to say user input going forward, and where the user input does not necessarily have to be human. One important thing to note is that prompts do not necessarily refer uniquely to specific entities. In other words, there can be ambiguity because multiple masks may be compatible with a given prompt. We'll talk about this briefly when we talk about the model. At a high level, this is what the SAM1 model architecture looks like. It's a two-part design, with the first part being an image encoder, which is just a vision transformer that creates a one-time image embedding, which then goes into the decoder, which is relatively lightweight and has the objective of creating a valid segmentation mask given the prompt and image embedding. And as mentioned previously, prompts can be clicks, boxes, imprecise masks, or even text. Clicks tend to be the most commonly used. When given only a single click, there can be ambiguity in the object of interest. For example, in the case of the scissors here, a click on the handle can be compatible with a segmentation mask corresponding to the whole scissors, the handle, or a part of the handle. So in the case of a single click, the model predicts 3 masks along with the score. When there are multiple clicks, the ambiguity tends to be resolved and only one mask is predicted. I'll talk more about the decoder later when explaining some of the changes we made for SAM2. Next, we'll talk about the data the model was trained on. SAM1 was trained on the SA1B dataset, which was the largest image segmentation dataset released to that date. It has over 1 billion masks on 11 million high-resolution images with high coverage over many domains and objects. All right, so SAM1 works really well for images. Why do we need SAM2? Well, images are only a static snapshot of the real world, which is complex and dynamic. If we want a truly universal visual segmentation system, it should apply to both images and videos. And in videos, what we want is a spatiotemporal mask or a masklet. Being able to get a masklet in videos by prompting has many real-world use cases. It can be useful, for example, to swap out the background for editing videos or in a video call. It can be useful in autonomous driving applications. It can be useful for face blurring, gaze-based detection in AR systems, and many other applications. And while I'll be focusing in this talk mainly on how we solve the various research challenges to make SAM2 happen, there are clearly many applications in industry. So why wasn't this possible before? In other words, what are some challenges standing in the way of building a universal visual segmentation model? We can break down the sum of these challenges coarsely along task, model, and data axes. On the task side of things, segmentation videos can be much more complex and challenging. There can be many similar looking objects that might occlude each other. They might go out of frame and come back after some time. There might be rapid changes in appearance because of changes in viewpoint, or maybe because there was a change in the shape of the object. There can be fast motion and motion blur. On the model side of things, one characteristic we would like to have is an efficient real-time streaming model to enable the broadest set of applications. Besides efficiency requirements, a big capability gap exists. Specifically, existing video object segmentation models are not interactive, meaning that the input is just a mask on the first frame that is propagated to the rest of the video. But requiring a mask is not particularly convenient, and the model not being interactive means that we cannot easily fix errors or make refinements. We can achieve some limited interactive ability by combining existing VS models with SAM1, but then the SAM1 is the component that's responsible for interactivity will lack spatiotemporal context that an end-to-end model can have. Such models can also tend to be brittle to domain shifts, segmenting parts, and handling occlusions. On the data side of things, especially on training data, existing data sets have a lot of limitations. One, there's not a whole lot of it. And the existing data tends not to be very diverse and is typically restricted to a small set of common object categories. It also tends to be focused on whole objects over parts. And overall, a lot of data is simply not very challenging, with not much changes in appearance, not too much occlusion, not too many similar confusable objects being present, and so on. All right, so we've discussed three key components of SAM1 and the challenges that they present for videos. I want to briefly mention the data engine as another key component of SAM1's success, which helped iteratively improve the model and the data. At a high level, this is the blueprint that we will follow for SAM2, leveraging lessons from SAM1. Okay, with that, let's dive into SAM2. Following the strategy of SAM1, we introduce a promptable visual segmentation task, a unified model capable of promptable visual segmentation on images as well as videos, and the SAV dataset, which is the largest video segmentation dataset to date. We'll talk about each of these. Before we talk about the promptable visual segmentation task, it will be helpful to talk about a related, historically common task to contrast it with. So in this semi-supervised VOS task, the input is a mask on the first frame and the video. The model is then expected to propagate the mask to the whole video, producing masklet over all frames. However, as I've mentioned previously, masks are not really convenient and practical, for example, compared to clicks. Moreover, this task is not interactive, and so there's no room for correcting errors or making refinements. The promptable visual segmentation task, in contrast, is fundamentally an interactive segmentation task. The user can prompt the model on any subset of frames using clicks, masks, or bounding boxes. The model is then expected to propagate to produce a masklet over the entire frame. The user can then make corrections or refinements iteratively as many times as necessary until a valid masklet is obtained. So here's an example video that shows this in action. So for example, here the left shoe and the football are expected to be segmented, and maybe there's a mistake at some point down the line where a negative click can fix it. So this is an example of interactive refinement. Notice that this task generalizes the SAM1 task for images as well as videos. Here, image is basically just a special case of a video with one frame. Notice also that the task definition is exactly what you'd expect from a human annotator. And being able to interactively prompt a model to get the result that you want can be a very powerful paradigm, as we've seen from large language models. At a high level, the SAM2 architecture can be thought of as the SAM1 architecture plus memory components. Now, the SAM1 architecture looks something like this. There's an image encoder, prompt encoder, and a mask decoder. In the example here, the target segmentation is the plume of the rooster. SAM2 differs from SAM1 in these blue boxes, which are the memory components. These have the purpose of storing information about previous frames of the video, as well as storing information about user interaction. This information is then used to segment the current object in the current frame. When applied to images, the memory components are empty and the model reduces to the SAM design. For video, the memory components come into play. The model is applied frame by frame in a streaming approach. Every new frame comes in and goes through the image encoder, which is a hierarchical vision transformer that accepts high-resolution input of 1024 pixels. Then there is the memory attention. The memory attention's job is to condition the current frame's embedding on information from previous frames, as well as on user interactions, using memory stored in the memory bank. The output of the memory attention is then passed to the decoder, which is used together with prompts, if there are any on the current frame, to produce a mask for the current frame. The memory encoder then takes the output mask and fuses it with the information from the image encoder to create a spatial memory, which is then placed in the memory bank for use in segmenting subsequent frames. Typically, we store spatial memories from the past 6 frames. The memory bank actually also has another kind of memory called the object pointer memories that I'll be talking about when we discuss the decoder. These are much lighter memories, and we can store many more of them. Okay, let's talk about the decoder. We won't have time to go into too much detail, and I'll have to point you to the paper, but I want to quickly discuss some salient points. The job of the decoder is to take the image embedding for the current frame, as well as any prompt if present on the current frame, and produce an output mask for the current frame. For video, remember that the image embedding is already conditioned on memories from the memory bank. Another difference for video is that there are 2 additional outputs, an occlusion score and an object pointer. The object pointer is a succinct representation of mask information in current frame and is placed in the memory bank. The occlusion score predicts whether the object being segmented is present in the current frame. Both of these are quite important, and we've already discussed object pointers being present in the context of the memory bank. Before we discuss the occlusion score, as promised, let's talk about ambiguity. Recall that in the image setting, a prompt could be ambiguous. In video, ambiguity can extend across frames and needs to be handled appropriately. More specifically, in video, ambiguity is even more challenging because more of the object can come into view later on. In such a case, predicting just a single mask for each time step could then result in artifacts due to collapse of multiple compatible masks. To mitigate this, SAM2 predicts multiple masks at each time step. If the user does not resolve the ambiguity by providing more prompts, by default only the highest scoring mask is then propagated, although other choices of what to propagate are possible. I mentioned that the decoder also predicts an occlusion score. This helps the model be more robust to occlusion by other objects or in the event that the object leaves the frame. It can also be used to potentially select memories which are going to be included in the memory bank in the event of long occlusions. So we talked about the task and the model. Let's talk about the dataset. How did we build the largest video segmentation dataset to date? We start from about 50,000 in the wild videos with over 200 hours of video spanning 47 different countries. To annotate these videos with masklets, following the strategy in SAM1, we build a data engine. The goal of the data engine is to improve both the model and data iteratively. The idea is simple but very powerful. At a high level, it looks something like this. We train a model on existing data, which is then in turn used to annotate more masklets and more videos. Human annotators can then make corrections in the loop. This is fast because they're using an interactive model to make corrections or refinements. The resulting data is then higher quality, higher quantity, and focused on fixing failure cases of the model. We can then train a new model on this data, resulting in an improved model. And we can then repeat this loop several times to iteratively improve the model and data quality. In practice, our data engine evolved in several distinct phases. I'm going to have to point you to the paper for details. At a high level, our annotation tasks that we converged on looked something like this. A challenging object is selected for annotation. An object could be challenging for many reasons. There could be fast movement, maybe there's occlusion, maybe it's a part instead of a whole object, and so on. The object is then annotated using our model and interactively refined. The resulting masklet is then verified for correctness and quality. If it fails, then it's re-annotated until it's correct. Importantly, for each of these tasks, they're done by a separate annotator to maintain high data quality. If this was not the case, we found, for example, that the annotators might select an easy object, and thus the learning signal available from the resulting masklet would be low. As such, the design of the annotation tasks is in itself a critical research direction and needs to be treated as such. We customize the annotation task and tooling iteratively, Altogether, we implemented and tested 15 variations of the annotation task to reach the optimal final version. Altogether, the SAV dataset has almost 650,000 high-quality challenging masklets and more than 50,000 in the wild videos. This dataset is a critical ingredient to enabling the segment anything capability in video. All right, let's look at some results. We'll begin with some qualitative examples. SAM2 handles parts with ease. For example, the person's shirt here is the target object for segmentation. SAM2 gets this perfectly, while the baseline quickly leaks to include the person's face and sometimes the person's arm. SAM2 is a unified model for images as well as videos. Here's a qualitative example for images. On the right here is SAM2. With one click, it's able to segment out the object of interest, which is a fish. And on the left is the same example using SAM1, which gets not just the fish that we're interested in segmenting out, but an additional fish next. I should point out that this kind of a failure case is pretty rare for SAM1 as well, so this is slightly cherry-picked. Fundamentally, if you want to do quantitative evaluations, SAM2 is an interactive model, and quantitative evaluations need to reflect that. To do that, we simulate the user or demo experience. We do that by prompting the model using the ground truth region several times. We then propagate that to the end of the video. Then we pick the frame with the biggest error and make corrections and propagate to the end. We can repeat this several times, and then this can give us a measure of performance in an interactive manner. So what do the numbers look like? Here on the horizontal axis, the more frames that you prompt, we can see that on the vertical axis, the accuracy gets better. We measure accuracy on 9 data sets of video object segmentation, and these are all zero-shot. And you can see that SAM2 significantly outperforms the baselines. The baselines are also built by us and use SAM in combination with a tracker. And these are pretty strong baselines that were carefully tuned. Although not the focus of this work, we also evaluate the model on this historically common video object segmentation task with a mask input in the first frame, which is then propagated to all the other frames. And we can see that SAM2 enables a step change in performance, especially on the challenging test and val sets that we introduced, on which SAM2 performs significantly better than all previous methods. Notably, these include many object categories not present in existing datasets, as well as object parts. And so they better reflect a segment anything capability in videos than previous benchmarks. We also have a SAM 2.1 model, which I'll talk about later at the end, that further improves performance significantly. Many comprehensive evaluation and ablations are in the paper. I won't have a chance to discuss them all, but one interesting finding is that the performance as a function of masklets is shown here, and it does not saturate across numerous benchmarks, so there is room to push further. Now, SAM2 is a unified model, so it should work on images as well as videos. To measure performance quantitatively on images, we measure performance on 37 zero-shot image segmentation datasets. And we find that SAM2 outperforms SAM1 on most datasets, while being 6x faster due to a combination of modeling and data changes. So while SAM2 delivers a step change in performance in promptable visual segmentation, this is not a solved problem by any means. Many limitations exist stemming from occlusions, crowded scenes with similar objects, shot changes, some problems with small objects in some cases, segmenting out fine details, and significantly out-of-domain videos. I'll talk briefly about SAM 2.1 now, where we make further advances on top of SAM 2, mitigating some of these failure cases. So SAM 2.1 delivers significant performance improvements by doing some simple modeling changes. Specifically, we do some long context fine-tuning, handle occlusion in a slightly improved manner, and using mosaic augmentation to help with small objects. As a part of SAM 2.1, we also released a developer suite that should make building with SAM2 even easier. I'll talk about that in a minute. Okay, let's talk about the launch and some of the exciting real-world use cases from the community. SAM2 was released a few months ago, announced by Mark at SIGGRAPH. We were really excited to see a lot of community adoption and saw more than 200,000 demo users and many diverse external use cases. As a part of the launch, we released a very cool demo that allows you to upload your own video, track up to 3 objects, get real-time predictions, apply cool visual effects, and so on. Also, as a part of the launch, we released a very cool dataset visualizer. It allows you to visualize the data and annotations. You can also visualize when the objects become included in the UI, and you can filter in various ways. It's very cool. Please check it out. As a part of SAM 2.1 release, as I mentioned, we also released the developer suite, which includes code for the demo backend and front end, as well as training code to help the community build even more easily. I won't be able to highlight all of the exciting use cases, but I want to mention some of them. For example, SAM2 has been used together with Stable Diffusion to create image editing workflows. It has also been used together with detection models to enable segmentation using text. It's also being used to annotate data on platforms like RoboFlow. It's being used for science, for example, for 3D medical segmentation. It's being used in sports for tracking and re-ID. And here's some other cool use cases that are quite a bit out of domain. For example, tracking ocean eddies and volcanic eruptions. And as you heard from Ishan yesterday, SAM2 was also used in the development of MovieGen. And with that, I will end here. We're excited to hear about your use cases, so please don't hesitate to share with us on our GitHub if you use SAM2 to build something, or tag us on Twitter. We'd love to hear from you. There's still a lot of technical challenges that exist. We can't solve them all. So we're really excited to see what the community builds on top, and please reach out to us if you're interested in solving them with us. Thanks.